Hey guys! In this video we're going to continue with our introductory topics into the cosmology. We will go through a few definitions together, and then we will discuss one important variable which we will be using a lot as we delve deeper into the field. This picture that you see is quite cool. It's one of the it is the deepest picture that mankind has taken from our universe. If you wanna know more about this picture, please search what is written in the top, and yeah, it's good to know about this stuff. It's a very cool picture, to be honest. Yeah, I'm pretty pleased with it. So, in the last lesson, we saw our universe was smooth. So, from our observations, we can infer two properties of our universe: homogeneity and isotropy. Homogeneity means that every point in our universe looks the same with the other points in the universe, or there are no reference points or spatial locations in our universe. Or in one more interpretation, you can say, if you take one point of universe, you cannot really distinguish it if you translate it through the space from the other points in the universe, on the large enough scales, of course. The other property of our universe was isotropy. Isotropy means that our universe does not have a preferred direction. So if you take one chunk of it and then rotate it around through an angle, you wouldn't be able to tell the difference. So let's be clear here. These two properties come from our observations that have been made so far, They are not absolute, and they might be subject to change if our observations in the future show us a different thing. But from the best of our knowledge, the universe on large enough scales has these two properties. So that was our definitions. Now let's add a few more details to what we can observe from our universe, or our picture of the universe as we know it. This particular detail comes from the observations made by the American astronomer Edwin Hubble, Oxford and Chicago University. This Big Bang Theory stuff was all his fault, by the way, but from experimental point of view and verification, of course. So in 1929 he published his studies of our local vicinity. He measured the redshifts of our nearby galaxies. But before we go into what he did, let's discuss our very important variable which I mentioned earlier, redshift. The main interest in redshift for us physicists is to measure the redshifts of galaxies. The stars in the galaxies emit light, kind of like a black body, but not quite. Some of these wavelengths are absorbed by the elements that are present in the atmosphere of these stars. But this is not the only mechanism that experimenters can rely on to calculate the redshifts of the galaxies. For more details on that, please watch the video I've provided in the description to one of my favorite YouTube channels, 60 Symbols. These are real professionals from Nottingham University, by the way, if you didn't know that. But yeah, if these galaxies move away from us, they produce redshift, and if they are moving towards us, they produce blue shift. But I'm not gonna go into too much detail because you already know it. So let's discuss how we can measure these redshifts. Like many other things in science, we want to be able to give numbers to things, and in this case it is Doppler shift. We can introduce a variable which is going to be very useful for us later, and yet it is going to be dimensionless. and it is going to tell us how strong or weak these shifts are going to be once we put the corresponding variables in the relationship. This letter is usually denoted by the letter Z, and I have not seen any other letter that is associated with the meaning of this. So how do we come up with a variable like this? It's really easy. We just divide the difference between the observed wavelength and the emitted wavelength, and divide that difference by the original wavelength that was emitted. So if our observed wavelength was smaller than what was emitted, we would have the case where or Z would be less than 0, and we would get a blue shift, and that means that the galaxy that light was coming from was moving towards us. But if the observed wavelength was greater than what was emitted, so it was longer, then or Z would be positive, and that would be the case for the redshift. And that would mean that galaxy was receding from us, was moving away from us. So yeah, this relationship is one of those that unfortunately you have to memorize, I think. In my case, I had to. I'm completely against memorizing things, but there are things that I cannot really control. But yeah, anyway, so for, I don't know, remembering it, I think I always forgot. I will always forget which lambda I should divide this by, the observed one or the emitted one. So you want to go with the emitted one because it shows a physical characteristic. So the observed wavelength is going to change by the motion of the galaxy, but the emitted one is a physical constant. It is a characteristic of the mechanism that you're observing. So it is always going to be the emitted one you want to put there. For the case where if you don't know if this one is observed or emitted one, or this one is emitted or the observed one, you should know that you get a positive Z when you have a redshift, and so this one has to be larger than this one, so you know this one has to be observed, and this one is going to need to be the emitted one. So that's how you can deduce what the form of this relationship is going to be. So if you have problem with that, recall these, and you'll get to the right formula for x, z. So why all the physicists call z the redshift and not the shift or the Doppler shift? Well, that all comes from the observations that initially was done by the Hubble. We're gonna discuss his work later. We mentioned his name a bit earlier on, but we need this formula to discuss his work in more detail. But since this video is getting too long, I'm gonna do that in the next video. So yeah, that's all. See you later, guys. Bye.